5.6 Related rates. Related rate equations. Suppose that a particular p of xy is moving along a curve c in the plane so that its coordinates x and y are differentiable functions of time t. If d is the distance from the origin to p, then using the chain rule we can find any equation that relates derivative of d over dt to dx over dt and dy over dt. So if d was the square root of x squared plus y squared, we could take the derivative implicitly with respect to t. So we're taking the derivative implicitly with respect to a third or even a fourth variable. See, there's no t's in here, so we very much have to do this implicitly. So anytime we take the derivative of a variable, we will write the variable over dt. So here we took the derivative of d, there's the dt. We take the derivative of x, dt, and derivative of y with dt. Any equation involving two or more variables that are differentiable functions of time t can be used to find an equation that relates their corresponding rates. So example 1, finding related rate equations. Assume that the radius of a sphere is differentiable function of t and let v be the volume of the sphere. Find an equation that relates the derivative of v with respect to t and dr with respect to t. So in letter A, we need the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. We need to take the derivative of this equation with respect to t. So we have dv dt is equal to 4 pi r squared dr dt. In letter B, we assume that the radius r and height h of a cone are differentiable functions of t, and let v be the volume of the cone. Find an equation that relates all three of these together. The volume of a cone is, letter B, assume that the radius r and height h of a cone are differentiable functions of t, and let v be the volume of the cone. Find an equation that relates these three things together. In letter B, we need the volume of a cone, which is 1/3 pi r squared h. Now we need to take the derivative of this implicitly, so dv over dt is equal to, let's call this the first, and we'll call the second just h. So we have first times derivative of the second, which is dh dt, plus the second times the derivative of the first, which is 2/3 pi r dr dt. Example 2, a rising balloon. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder's elevation angle is pi over 4, the angle is increasing at the rate of 0.14 radians per minute. How fast is the balloon rising at that moment? So we have this person tracking a rising balloon, and that person is 500 feet away, and here is the balloon rising. We'll call that h, the height of the balloon, and here is the line of sight to the balloon. This angle is changing, so there's theta, but this is always 500. Now let's get some information. We know that the distance is 500, and it says at the moment the rangefinder's elevation angle is pi over 4. So we know that theta is pi over 4, but that angle is changing as the balloon is rising. The angle is increasing at a rate of 0.14 radians per minute. That means the change in theta with respect to time is equal to 0.14 radians per minute. How fast is the balloon rising at that moment? Well, the balloon is rising, its rate is dh dt, and that's what they want to know. Now we have to find some sort of equation that relates these three things. We have the tangent of theta is equal to h over 500. Well, now in order to introduce the d theta dt's, the dh dt's, we need to take the derivative. The derivative of tangent is secant squared theta, but then times d theta dt. And the right side, the derivative of this side, is 1 over 500 dh dt. Now we're trying to find dh dt. And so now we can plug in some values and solve for dH/dt. We have the secant squared of theta, and we're looking at the moment that theta is pi over 4. d theta dt is 0.14, so we're multiplying this times 0.14. And we need to multiply all of this times 500 to get the dH dt. We have 1 divided by the cosine of pi divided by 4 squared times 0.14 and then times 500. That's equal to 140. So we have 140, and that's going to be, let's see, is this in feet? Yep, feet per minute. Example 3, a highway chase. A police cruiser approaching a right-angled intersection from the north. All right, so we have this police car approaching an intersection from the north, is chasing a speeding car that has turned the corner and is now moving straight east. So it's chasing a car moving straight east. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? So we have this distance between the police car and the car that it's chasing. So right here we have the police, and we have this suspect that's running away. So let's call that the car, and the distance between them, let's call that the distance. Let's get some information. When the cruiser is 0.6 miles north of the intersection, so the P is 0.6 miles, and the car is 0.8 miles to the east, so the C, the car that the police is chasing, is 0.8 miles from the intersection. The police determine with radar that the distance between them and the car is increasing at 20 miles per hour. So that means the derivative of the distance with respect to t is equal to 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? So the derivative of p with respect to t is equal to, now watch this, you got to be careful, this is equal to negative 60, because this distance from the police car to the intersection is actually decreasing. This side is getting smaller. So we say that the rate is actually negative because of that fact. They want to know, what do they want to know? What is the speed of the car? So they want to know what dc dt is. That's the question. We have a right triangle here, so we can use the Pythagorean theorem. P squared plus c squared is equal to d squared. Now we want to plug in values when we can right away. Now we can only plug values in if the side is not changing, and all three sides are changing, so no values can be plugged in right away. We have to take the derivative first. So the derivative with respect to time is 2p dp dt plus 2c dc dt is equal to 2d and then the derivative of d with respect to t. Now we can just start plugging in values. Now everything can be divided by 2, so we don't really have to worry about the 2's. We have 0.6 times dp dt is negative 60 plus c, which is 0.8, times dc dt, and that's what we want to find out, so we can't plug anything for this, equals the d, we don't know that, so we need d times the derivative of d with respect to t is 20. Well, we can find the d because we know what p and c are, so we can find the d. We have p squared, which is 0.6 squared, plus the c is 0.8. That's 0.8 squared is equal to, we have d squared. We have 0.6 squared plus 0.8 squared. We need that value, which is 1, and the square root of 1 is 1. So d is 1. we have negative 36 plus 0.8 dc dt is equal to 20. 0.8 dc dt is equal to 56, and then dc dt is equal to, we need 56 divided by 0.8, and that's equal to 70 miles per hour. Example 4, filling a conical tank. Water runs into a conical tank at the rate of 9 feet cubed per minute. The tank stands point down and has a height of 10 feet and a base radius of 5. So this radius right here is 5 and the height is 10. How fast is the water level rising when the water is 6 feet deep? Well, they've told us that the volume is changing by 9 feet cubed per minute. They tell us that they tell us the radius and the height. So the radius over the height is equal to 5 over 10. And then finally they ask us for dH dt. How fast is the water level rising? They want to know that when the water is 6 feet deep. So when h is equal to 6 feet. The volume of a cone is 1/3 pi r squared h. Well, we want to find this rate. Given this rate, we need to take the derivative of this. But we have two variables. We want to get rid of those. And since we're trying to find dH dt, I really want to get rid of r. And we can use this proportion to get rid of r. We can multiply by h. r equals 1/2 h. So we multiply by h, and 5/10 is 1/2. Now we can replace the r with 1/2 h. The volume is equal to 1/3 pi times 1/2 h squared and then times h. So we replace the r. The volume is now equal to, well, 1/2 squared is 4, or 1/4, times 1/3 is 1/12, and we have pi h to the third. Well, now that we have just one variable over here, we can take the derivative. We have dv dt is equal to 1/4, or 3 times 1/12, that becomes 1/4, pi h squared, but then times dH dt. Now we can fill dv dt in with 9, and we're going to do positive because this cone is going to fill up, which means that the height is actually increasing and the volume's increasing, so that's going to be positive, equals to 1/4 pi times h. Well, we want to know all these values when h is 6, so we have 6 squared and then times dH dt. We have 9 equals, this is 36 divided by 4 is 9, so we have 9 pi times dH dt. Now when we divide by 9 pi, dH dt is equal to 1/pi, and that is going to be feet per minute.